very nice example. So, lots of times you hear people say, well, there's no examples of evolution occurring in the time span that we can see. What should you say to that? Well, I'd say something that's derogatory. I'd say that's absolutely wrong. You're completely inaccurate. So you can see it all the time. This is a very nice example of evolution in operation and natural selection as the driving force. So this is Piston ventillaria. It's called the pepper moth, all right? And so when you take a look at this moth over here, they have two morphs. They have skin color like we do, changes in it, yes? So they have a black morph with kind of gray speckling on it. They have a white morph with kind of gray speckling on it. They're the same moth. They're the same species. They eat the same stuff. They do the same things. They're both found together, and they're found in the woods in Europe. And so here's an example of them together. So you can see the black moth up there on the lichen. So this is a nice forest in the middle of Britain someplace. And they're looking at the trunk of a tree. In this circle right here, there's actually a white moth, and then there's this black moth right on it. And here's one that's on dark bark without the lichens, and you can see the black moth right here, and then the white moth right there, right? Okay. So that's the basic idea of what you observe when you see them in nature. Well, you can take a look at some historical data about the population size of these moths. And so, pre-industrial England, the first thing you notice is when people did surveys of these moths in the forests in England, there's lots of light morphs around and not that many dark morphs around. So the light morph is far outnumbering the dark morph in terms of the number of individuals who bear that particular trait. The Industrial Revolution in the 1850s, late 40s into the early 1850s. And so in this case, you go back and do the same survey, and all of a sudden it flips. And now it's all dark moths and hardly any light moths. 1952 was the Clean Air Act in Britain. They put scrubbers on the coal-burning stacks. When they did that, lo and behold, the population shifts right back. What causes that? Any idea? Pollution. So this is London. Before they did the institution of the Clean Air Act, think they needed it? Yes. That's what LA used to look like at times of the year sometimes. It was brutal. LA's a lot better than it used to be in the past. I remember when I was a kid, you'd go outside, it was literally like thick. You can see it was like, well, you can take 3 breaths today. That's all you get. That's your quota for the day. So it's pretty rough. But again, we've cleaned up a lot too. So pollution is really bad. Now what pollution does, if you take a look at lots of the trees, especially like the British forests, what you'll notice is naturally, a lot of times the trunk is fairly light colored. They have light colored trunks. And where you don't have pollution, is since it's fairly moist, you have these lichens. And the lichens are nice and white colored, right? They're real light. However, when you get pollution, you're burning coal. What settles out of the sky? Ash, right? All this kind of nasty coal dust. All this sulfur compounds. And they're what color? They're real dark. And they settle on the vegetation, and they coat the trunks, and they make them black. So, what's better, to be light or dark when you're on lichens? You want to be light. Why? Because you're camouflaged. That's exactly it. So the way it works is this. Who do you think eats these? Birds. They love them. Okay, that's a big meal. So, let's see. I was going to use that paper, but it's got disgusting gum stuck to it, so I don't think I will. I'm not sure it's my gum, though, so maybe it's a... So let's do this little trick right here. So here's pre-industrial England. Here's my tree. Who's easier to see? Who gets picked off by the birds? These guys get picked off, picked off, picked off. What's the better trait here? This trait is giving you what? An advantage in survivability, and if you survive, you get to what? Reproduce. So who passes on more traits to the pool of genes in the next generation? Pretty soon the population is almost exclusively this. But now it's polluted, right? So now you're shifting. You've covered up all that white, kills all the lichens because they're intolerant to pollution, so they all die and fall off the trees. And now I'm looking like this. Who survives now? So these guys here are surviving, therefore they get to do what? Reproduce. And what about these guys? They see it, they get picked off. Now you put scrubbers on the stack, what do? You flip it right back. Boom. Now here's the thing. If you didn't have the variation, what would have happened? Extinct, right? No variation, see ya. No variation, see ya. That's the advantage of variation. That's its purpose, right? It's an arsenal against environmental change. That's the whole idea of it. So this is showing how directional selection is skewing from one side to the other in terms of the particular trait, from very dark coloration to very light coloration, and back and forth, depending on the environment that that particular trait is expressed in. That's directional selection operating over the span of not that long, right? 100 years or so. We could even do it shorter than that. So this has actually been replicated in the lab. These were the Kettlewell experiments in the 50s. They're classic experiments in evolution. What they do is they use mark and recapture techniques for these particular kinds of moths. They release light and dark moths to fluted and unfluted areas, and this is what they found. More dark moths were caught, recaptured in fluted areas, and more light moths were caught or recaptured in unfluted areas. Does that make sense? Absolutely. What happened to all the light moths that were released into the fluted areas? They died because they were picked off by the birds, so when you went to collect them, who was left? Just the dark ones. Same thing for the unfluted areas. You went out there, who was picked off? All the dark moths. When you went to collect, who was there? Just the light moth. And so this is done quick. This was literally over like a season. You can see these kinds of changes that are occurring. With the next generation showing that change in terms of increases in the frequency of certain moths. All right? All right, so birds capture more light moths around the polluted areas, more dark moths in the unpolluted areas. It's directional selection and operation. So if anyone ever says there's no examples of evolution that we can call as a scientist to give an example operating in the time span that we can see, again, completely wrong, inaccurate, and false. Let's talk about some examples of this operating in the world in not such nice ways with human beings that we unfortunately drive. And so, directional selection can be expressed cleanly with pesticide resistance and different kinds of nasty insects that we do not like because they eat our agricultural crops and reduce our yields. Chemical pesticide resistance in agriculture has been driven by directional selection. So, what we see is that resistance can be quite heritable and be passed on generation to generation. That's a big problem for us. So the chemicals act as the selecting agents, favoring the most resistant forms. Today, there's greater than 450 species of pests that are resistant to one or more commercially available pesticides. And that's our fault. So for example, if we were a bunch of pests sitting, this is our agricultural crop, and I spray the field with some pesticide, is it going to kill them all? There's going to be natural variation in that population, and certain individuals will be resistant. You will kill everything else, but what will happen in the next generation? The individuals that survive will reproduce and pass on the traits, which are the traits of resistance to the next generation. And since insect populations can replicate themselves quite quickly, before you know it, 2 seasons now, I hit it with the same pesticide, and what happens? Nothing. They're all surviving. Okay? So what happens is the expensive pesticide that I've manufactured and now putting on my crops is completely worthless. And I have a bunch of pests that are just laughing at it as they chomp away on my crops. Well, that's a nice example of directional selection. We're driving this particular trait one way. And there's another problem with this, however. Pest populations are typically pretty large. Their predator populations are what in comparison? Smaller. The main predators of insect pests are what? Other insects. That's exactly right. Does the chemical distinguish between the pest you want and the pest you don't want? It treats them exactly the same way. So here's the thing. If I have 2 million pests, but I only have 2,000 predators, and I hit them with the same chemical compounds, what can happen to my predator group? I can kill them all. But the pests, because they have a larger group with more variation probably within that group, survive it. Now they come back, not only are they resistant to the pesticide, but they're also what? There's no predators to control them naturally because I wiped them all out. That's problematic. That's called pest resurgence. It's a common problem in common farming practices, right? Here's another example. A lot of you guys are planning to be doctors, correct? Right? You're heading into the medical fields. Antibiotic resistance is a major dilemma that faces us as a species right now. This is our own fault too. We have badly mismanaged and misused antibiotics, which are a wonder drug. Antibiotics have really only been around since the 50s, but we've already decimated them to the most of our necessities in terms of our needs for them. So what's happened is evolution of microbes to become resistant to antibiotics has far outpaced our ability to create new antibiotics to confront them. So the real benefit, now we haven't spent any time talking about prokaryotic evolution, just because I don't have the time to do it. I wish I did because it's super cool. But their main advantage is the ability to evolve rapidly and quickly. How? They don't have any sexual selection. How can they do all this stuff? It's the ability to replicate quickly, but also the ability to do what? To share genetic material among each other, right? That's a massive advantage. I don't have to wait for a mutation to occur. I can grab someone else's mutation and use it. That's a powerful thing, right? So by the ability to shift these resistances around from individual to individual, you can quickly turn a population that can be decimated by antibiotics to be completely resistant within a couple generations. And we see that time and time again. So right now, we're seeing it in typhoid is making a resurgence. Gonorrhea is actually making a massive resurgence in their forms of gonorrhea that are completely resistant to all known forms of antibiotics. And if you get that, that's a sexually transmitted disease that's not going to kill you, because we have no way to treat it. Pretty nasty business, yes? So how have we let this get so out of control? We've misused this gift. How have we done it? Overprescription. Often, doctors have definitely been at fault here by overprescribing antibiotics when they're not required. They look at your throat, I got to scratch your throat, doc. Give me an antibiotic. No, here you have some. Here's the basic general antibiotic. Go for it. Maybe it was just not bacterial at all. Did they do a test? Did they give you a swab? Did they cultivate anything? Right? There's no cultures. So maybe it was just strictly viral. Are the antibiotics worth anything? They're not going to do anything to to cure your illness, but what are they going to do? They're going to start to select for antibiotic-resistant bacteria within your own body. So when you really have a problem bacterially, and now you hit with the antibiotics, what's the problem? They won't work. So that's a major dilemma. Here's another one. Because of the nature and the way that antibiotics work, you often have to take a spectrum of them, a course of them, right? And so often that can be anywhere from 7 to 14 days, 21 days in some cases, right? You got to take the whole darn course. Because what happens is you start to feel good after 2 or 3 days sometimes, right? I'm day 5, I feel great. I got to take another 5 days of this. It's making my stomach hurt. I hate them. They're making me nauseous. I'm not taking them. I feel great. Good idea? Hell no. Because if you do that, what have you just done? You didn't kill them all. All you did was weed out the weak, and you left the strong, right? And now what are those strong going to do? They're going to reproduce and pass on that resistance. Even if they were semi-resistant, they're passing it on. If they were semi-resistant, you would have killed them off with a 10-day course of antibiotics. But you allow them to survive, and they get stronger and stronger. Now you go back, it's 2 weeks later, and you're like, oh, my throat's still killing me. And the doctor says, well, take your antibiotics? Yeah, I took them, and you lie. Right? Yeah, I took them. It's all, well, let's try it again. And they don't work at all. And now you're on another type of antibiotic, which is stronger, and you're running out of options when you need it again. The problem is we used to have layers and layers and layers of antibiotics that you could take. Super general ones, more specific ones, really, but then kind of the end course ones. Those layers have disappeared. We're getting thinner and thinner in terms of our layers. Sometimes it's only 1 layer thick, 2 layers thick. We got nothing after that. Why is that? They evolve at a faster rate than our ability to create the antibiotics. Antibiotic creation is a very expensive product. It's really expensive to produce and research. The time of antibiotics is coming to an end. So if you're thinking about being a medical doctor, especially involved in research, come up with something quick because we're running out of time. It's really coming down to that. It's like Victorian England. You'll be back there pretty soon. You got a hangnail, it's infected. Oh, let's cut your finger off, all right? Take a look at that right there. That used to be a foot. So those are maggots on the foot. And it's not that that person had a fly that landed there and the maggots just magically were on the rock, but that's the last line of defense. This is basically a resistant form of bacteria. It's a staph. It's found in lots of hospitals today. HRSA, okay? So in this case, basically what it's done is nothing worked on this individual. All that was left to do is go back to Roman times. What do? Pack in the maggots to clean out the dead and decaying flesh. That's what was left. I'd rather have antibiotics that work, all right, than have to resort to that. But that's all there was. So again, even today, the last line's falling. Here's an example. If you have something that's like a typical, let's say, a venereal disease like chlamydia, they used to treat that with really common antibiotics. Today, they treat that with like ciprofloxacin. You know what ciprofloxacin used to treat? Anthrax. That's a big difference in change, don't you think? And that's just over maybe 10, 15 years. That shows you the decay and the quality of our antibiotics' ability to deal with problems. All again driven by directional selection. Us as the selecting agent, right? Using antibiotics to do so. All right, here's the last one. This is disruptive selection. In this particular case, you have phenotypic characters at opposite extremes of the character distribution spectrum, and they're favored at the same time, and intermediate forms are selected again. So what's the difference between this and directional? In directional, it was either that side or this side, but in disruptive, it's both extremes and not the middle. Does that make sense? Directional is this or that. Disruptive is both ends, not the middle. Okay? So what are the basic conditions for this? It's disruptive for, the name actually means something. Typically it means that the environment is changing rapidly or significantly in some way, biologically, chemically, or physically. It typically occurs in environments that are shifting around a lot, and the fitness for a particular genotype is higher on one side, that side, but not the middle. Okay, this side and that side, not the middle. And it changes with a given environment. So here's an example. We're going to start out with our continuously variable trait. A plot is an up-shaped relationship, but notice the positive contributions to the pool of genes of the next generation here. Where are they at? They're on the sides. The middle is selected against. So over time, what will this look like? It'll be a bimodal curve, right? Two peaks down in the middle. Since this is also a disruptive event and it typically is severe, it has a tendency to do a number on the number of individuals as well by decreasing them. So in this case, also notice the time period. It's what? It's short. It happens quickly. It's not like a multi-generational thing. It happens very quick. It's a rapid change in the environment which drives it. So how do I know what I'm looking at if I was to give you an example graphically? The time period is long and the mean does not shift. What is that? What kind of selection? The time period is long and the mean does not shift. Stabilizing selection. The time period is long, but the mean shifts to the left or the right, but not both. Directional. The time period is short, the mean is selected against, and the extremes are selected for. That would be disruptive. So what's an example of disruptive selection? Well, there's a really nice classic example of that. It deals with this particular bird. So this is called the black-bellied seed cracker finch. Why is it called that? Because it has a black belly, and it cracks seeds, and it's a finch. There you go. Again, not the most inventive name, but very descriptive of the animal itself. Okay? When I look at this particular bird, which is found in Africa, the first thing I notice are there are two very distinct morphs of the bill. So in this case, we have a small-billed bird and a big-billed bird. That's actually quite difficult to say. All right? I want you to say that fast. That's tough, right? Okay, so we have one that's small, one that's large, but we hardly see anything in the middle. Okay, what's your question then? Why? So when we look at this, the first thing I see is something about their behavior. The small-billed birds eat lots of small, soft seeds. And the big-billed birds eat these large, kind of rough, tough-coated seeds. So they're eating very distinctive food sources. Same exact animal, but they're feeding on different things, different shapes of the bill. So this is the way it works. Seed cracking, the ability to crack seeds, is directly related to the survivability of the birds. Disruptive selection eliminates birds with an intermediate-sized bill. You don't see a lot of them. Well, why not? Because the environment of this bird is quite unique. So when you take a look at the pictures over here, that's the environment. Half the year it's a flooded forest. It's mostly an aquatic environment. It's all swampy and marshy. And then the trees kind of protruding up. And then it dries out super fast, and then it burns. Right? So it's a really weird environment that's shifting radically between two different kinds of environmental conditions. Do you think it's easy to be a generalist kind of in that setting like that? No. So let's think about it from the perspective of the trait that's being selected upon. So the first thing is we saw the small-billed birds eating the small little seeds that are soft. And then the big-billed birds eating large seeds that are big and tough. Where do you think you'll find those big seeds? What season? The burning season. That's it. Because the seeds have to be what? They got to be strong and tough with a thick coat to withstand getting burnt, right? When do you find the small little soft seeds then? When it's the wet season. That's when they're plentiful. There's no need to be protected because there's plenty of water around. Now here's the trick. If I have a big bill, I pretty much stink at eating the small size seeds. My bill's too big and they're hard to manipulate. They're too small. However, you give me a big seed, I'll crack right through it and grab it. If I'm a small-billed bird, I can eat the little ones, no problem. But if I try to eat that big seed, I can't crack through it very efficiently. It takes me a long, long time. I got to work at it. So what part of the year are the big-billed birds doing great? During the dry season, when it's burning. And what part of the year are the small-billed birds doing great? During the wet season. Now, what happens to the small-billed birds in the dry season? Their trait is what? Maladaptive or adaptive? It's maladaptive. What happens to the frequency of them? It goes down, 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 down. But before they can be driven to extinction, what happens? The season switches. Now who's the loser? The big-billed birds can't do anything, but the small-billed birds get all the food. So their numbers go down, 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 down. Before they can be eliminated, what happens? It goes back again. Now here's the thing. Well, why not just be an intermediate-sized bill and eat them both? Because you can't eat either very well. Because you stink of them both. It's such an extreme dichotomy that if you're in the middle, you don't do a good job of either. So basically, being intermediate is no different than being big in the wet season, and being intermediate is no different than being small in the dry season. So if I'm an intermediate-sized billed bird, am I doing well in the wet season? No, I'm getting pounded. And what happens in the dry season? I'm not doing well either. None of my traits are being passed on. My survivability reproduction is poor in both conditions. So what happens? They separate. Intermediate forms of the trait are selected against. What's selected for? The extremes of the trait. That's a really clean example. So let's just review. So again, wet season flooded, dry season burns. Small billed in the wet, large billed favored in the dry. During the dry season, the soft seeds go down, small billed competitive disadvantage increases. That means their mortality rate goes way up. The opposite occurs during the wet season. The hard seeds go down, the large billed competitive disadvantage increases, and therefore does their mortality. Intermediate-sized billed birds do poor at both seasons. They do not pass on that trait with any frequency. That leads to disruptive selection, creating the morphology that we see in this population. There's a nice example of it. Have a nice day. We'll cover the last slide.